May 12, 1943, near Wadi Akarit, Tunisia. Oberleutnant Klaus Hoffmann stood beside his disabled Panzer IV, watching British engineers work on the opposite bank of a wadi that his company had assumed would delay the 8th Army for at least 3 days. German intelligence had confirmed the wadi was 45 meters wide with unstable banks. Every bridge within 20 kilometers had been destroyed during the retreat. Hoffmann's company, down to 6 operational tanks, had positioned on high ground specifically to ambush British forces as they attempted a slow, vulnerable river crossing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 3 hours after the first British vehicles arrived, Hoffmann watched a complete bridge span the entire wadi. Trucks were already crossing. Within 90 minutes more, Valentine tanks followed. His position, carefully chosen to exploit what should have been a week-long British delay, was now flanked. By nightfall, his company was in full retreat. Hoffmann would survive the war and spend the next 40 years trying to explain to anyone who would listen that what he witnessed that day seemed impossible, not difficult. The bridge had appeared as if conjured from nothing. Panels assembled like children's building blocks, erected without cranes or specialized equipment by ordinary soldiers who seemed to be following instructions so simple that no engineering expertise was required. Hoffmann had been trained at the Wehrmacht's armor school in Putlos. He understood field engineering. What he watched violated everything he knew about bridge construction. The German military understood river obstacles. They had based defensive planning across North Africa, Italy, and eventually Western Europe on the mathematical certainty that rivers meant time. Time to regroup, time to establish new defensive lines, time to bring up reinforcements. A destroyed bridge meant Allied engineers needed 2 weeks minimum to construct a replacement capable of supporting armor. It was taught at every officer training school. It had been verified through combat experience against British forces in France in 1940, against Soviet forces in Russia from 1941 onward. Then, in 1942, that calculation became catastrophically wrong. The weapon that destroyed German defensive planning was not a tank, not an aircraft, not a wonder weapon born in secret laboratories. It was a modular bridge system designed by a quiet British civil engineer named Donald Bailey, a man so obscure that German intelligence files contained virtually nothing about him until after the war. Bailey's design replaced 2,000 years of bridge-building tradition with something revolutionary. Every component was identical and interchangeable. Every connection used the same simple pin and hole system. Any 10 soldiers with minimal training could assemble a bridge strong enough for 40-ton tanks using only hand tools. The implications were staggering. What had been a specialized engineering task, requiring weeks of work by trained specialists, became a routine operation completed in hours by ordinary infantry. German defensive doctrine, carefully constructed around the assumption that rivers meant predictable delays, collapsed. The British could now bridge obstacles faster than German forces could organize effective defenses of those crossings. Speed, not strength, became the decisive factor, and speed was something the Bailey Bridge delivered with mechanical precision. The story of how this happened begins not with dramatic combat, but with a fundamental rethinking of what a military bridge actually needed to be. April 1940, Christchurch, England. The military engineering experimental establishment occupied a sci-fi collection of buildings that had once been a Victorian-era factory. Donald Coleman Bailey worked in an office with a drafting table, a slide rule, and a growing conviction that every existing military bridge design was fundamentally flawed. Bailey was 40 years old, a civil engineer who had spent his career designing roads and municipal infrastructure. He had no combat experience, no military decorations, no connections to the brass at the War Office. What he had was 15 years of watching construction crews struggle with unnecessarily complicated bridge designs. Traditional military bridges required custom-fitted parts. Each component had unique dimensions. Assembly demanded specialized tools and trained engineers who understood complex load calculations. Lose one critical piece, and the entire bridge became useless. build it incorrectly, and the bridge collapsed under load, killing everyone on it. Bailey asked a question that seems obvious only in retrospect. What if every single component was identical? What if the bridge design eliminated all custom parts, all specialized tools, all requirement for engineering expertise in the field? The panels Bailey sketched measured 3 meters long and 1.5 meters tall. Each weighed exactly 270 kilograms, heavy enough to be structurally sound, light enough for 6 men to carry without mechanical equipment. The genius was the lattice structure. Each panel contained holes at precisely measured intervals. Every panel connected to the next using steel pins that dropped straight down through matching holes. No bolts, no welding, no mathematics required at the construction site. The design had already done the engineering work. Soldiers simply lined up holes and dropped pins. By December 1940, Bailey had built his first prototype. Military observers arrived expecting another incremental improvement over existing designs. What they witnessed was revolutionary. 12 soldiers with basic instruction assembled a 30-meter bridge in under 3 hours. Then Bailey demonstrated the real innovation. The modular system meant panels could be stacked vertically or placed side by side to increase strength. Need to cross a wider gap? Add more panels lengthwise. Need to support heavier tanks? Stack 2 or 3 layers high to create a reinforced truss. The same basic components worked for a 10-meter footbridge or a 60-meter vehicle crossing capable of holding a 40-ton Churchill tank. The British Army ordered immediate production in early 1941. By 1942, factories were stamping out 25,000 panels per month. Each panel was manufactured from high-tensile steel, using standard industrial processes. This was not custom engineering anymore. It was mass production, applied to military bridges. The Americans recognized the value immediately and began producing Bailey panels under license in 1942. By 1944, the United States had manufactured enough Bailey bridging equipment to stretch from London to Moscow if laid end to end. The speed advantage was staggering compared to traditional methods. During Operation Husky, the invasion of Sicily in July 1943, British engineers used Bailey bridges to replace 55 destroyed crossings in 3 weeks. In North Africa, the 8th Army built Bailey bridges across wadis that could support 30-ton tanks within 4 hours of reaching the obstacle. General Dwight Eisenhower later called the Bailey Bridge one of the 3 most important technological contributions to Allied victory. Alongside radar and the C-47 transport aircraft, Field Marshal Bernard Montgomery was more direct. Without the Bailey Bridge, we should not have won the war. But raw speed was only part of the story. What made the Bailey Bridge strategically decisive was how it interacted with German defensive doctrine. The Wehrmacht had planned defensive lines across Europe based on natural obstacles, rivers, gorges, canals. These barriers channeled Allied advances into predictable crossing points that could be fortified and defended. German engineers had pre-wired thousands of bridges for demolition. Blow the bridges, fall back to prepared positions, and force the Allies to spend weeks building replacements while German forces regrouped. This strategy had worked brilliantly in 1940 during the French campaign. It had worked against Soviet forces throughout 1941 and 1942. Then the Allies arrived in North Africa with Bailey bridges, and suddenly destroyed crossings became temporary inconveniences rather than strategic barriers. German forces would destroy a bridge and retreat to defensive positions, expecting a 2-week respite minimum. British engineers would arrive with Bailey equipment and have a functioning bridge operational in 6 to 8 hours. German defensive positions, carefully sited to overlook what should have been a major construction effort, found themselves flanked before they could effectively engage. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The psychological impact on German forces was profound. Oberst Heinrich Göckel commanded a combat engineer battalion in Tunisia during 1943. His post-war memoir, written while in British custody, described the creeping realization that fundamental assumptions about defensive warfare had become obsolete. "We would blow bridges according to established doctrine," Goeckel wrote. "Our commanders would plan defensive positions assuming the enemy needed 10 to 14 days to restore the crossing. Then we would watch British soldiers, not specialized engineers but ordinary infantry, assemble bridges in hours. Our defensive positions became traps. We were sighted to defend against an engineering effort that never materialized. By the time we recognized the situation and attempted to reposition, British armor was already across and moving to encircle us." The technical specifications of the Bailey Bridge help explain why it was so effective. The standard panel measured 3.05 meters long by 1.42 meters high. Each panel weighed between 265 and 275 kilograms, depending on manufacturing tolerances. The lattice design used triangulated bracing, which distributed loads efficiently across the entire structure. This meant the bridge gained strength not from heavy materials, but from geometric design. A single-story Bailey Bridge, called single-single in British nomenclature meaning single panel height and single panel width, could span 30 meters and support 9 tons. Stack 2 panels high, and the same span could support 30 tons. Stack 3 panels high, and the bridge could handle 54 tons, sufficient for the heaviest British tanks. The mathematics were straightforward and had been pre-calculated. Engineers in the field did not need to perform structural analysis. They simply consulted standardized tables that specified panel configurations based on span length and expected load. Construction methodology was deliberately simple. The bridge was assembled on one bank, then pushed across the gap using a launching nose, a lightweight frame that extended beyond the bridge structure to reach the opposite bank. As sections were completed, they were pushed forward. The launching nose distributed weight across the incomplete span, preventing collapse during construction. Once the bridge reached the far bank, the launching nose was removed, and the bridge was ready for traffic. This system eliminated the need for scaffolding, temporary supports, or work in the middle of the gap. All construction happened on safe ground. This reduced casualties during construction and dramatically accelerated the building process. A trained Bailey Bridge company could construct a 30-meter single-story bridge in 3 to 4 hours with 40 men. A 60-meter double-story bridge required approximately 8 hours with the same crew size. Compare this to traditional bridging methods. A timber trestle bridge of similar span required driving pilings into the riverbed, cutting and fitting lumber, and constructing supports in the water. This process took days and required that work crews operate in the obstacle itself, fully exposed to enemy fire. Steel truss bridges required cranes, specialized assembly crews, and custom-fitted components. Construction time ran to weeks. The Bailey Bridge changed the tactical calculus of river crossings entirely. American forces adopted Bailey bridges with enthusiasm bordering on obsession. By 1944, every American armored and infantry division included organic engineer battalions trained in Bailey Bridge construction. The U.S. Army produced detailed field manuals with photographic step-by-step instructions. Soldiers who had never seen a bridge built could follow the manual and produce a functioning structure. Training emphasized speed and standardization. Engineer companies practiced Bailey Bridge construction repeatedly until every man knew his specific role. The process became choreographed. Panel carriers moved in sequence. Pin insertion followed a specific pattern. The launching nose advanced in coordinated pushes. During training exercises at Fort Belvoir, Virginia, and Fort Lewis, Washington, engineer battalions competed for speed records. The fastest documented training construction was a 45-meter bridge, completed in 2 hours and 17 minutes. This level of proficiency meant that by the time engineer units deployed to combat theaters, Bailey Bridge construction had become routine. The psychological confidence this created cannot be overstated. Engineers knew they could bridge any gap they encountered. Infantry commanders knew destroyed bridges would not stop advances. Logistics officers could plan supply routes, assuming bridges would be replaced almost immediately. German forces had no equivalent system. The Wehrmacht used various bridging equipment, including the Brückengerät B and later the Brückengerät J, but these systems were heavier, more complex, and required specialized equipment to deploy. German bridge construction typically took 2 to 3 times longer than Allied Bailey Bridge construction for equivalent spans. By 1944, this disparity had become strategically significant. The first major test of Bailey bridges under sustained combat conditions came during the Italian campaign, September 9, 1943. Allied forces landed at Salerno. German forces, commanded by Field Marshal Albert Kesselring, implemented a defensive strategy based on natural barriers. The Italian peninsula offered ideal defensive terrain. Rivers ran perpendicular to the Allied axis of advance. Mountains channeled movement into predictable valleys. Kesselring's plan was straightforward: destroy every bridge, defend river crossings, and force the Allies into costly frontal assaults against prepared positions. The plan was sound according to traditional military engineering. It failed because it assumed bridge reconstruction would require weeks. British and American engineers brought Bailey equipment ashore with the initial assault waves. Within 48 hours of landing, Bailey bridges were spanning blown crossings. German defensive positions, carefully sited to dominate approaches to destroyed bridges, found themselves bypassed as Allied engineers built new bridges at alternate sites that German forces had not fortified. Major Werner Bathe commanded a Wehrmacht engineer company tasked with demolition and defensive engineering in Italy. His post-war interrogation, preserved in U.S. Army historical files, provides detailed German perspective on facing Bailey bridges. "We would conduct textbook demolitions," Bathe stated. "We destroyed bridges so thoroughly that reconstruction seemed impossible. Then we would establish defensive positions commanding the destroyed crossing. 12 hours later, sometimes less, we would observe Allied forces crossing on new bridges built upstream or downstream from the original site. Our defensive positions became useless. We were defending destroyed bridges, while Allied forces crossed on new bridges we had not anticipated." The mobility of Bailey bridge equipment was crucial. An Allied engineer company could transport enough Bailey panels on standard trucks to build a 60-metre bridge. This meant they were not limited to rebuilding at existing bridge sites. If German forces fortified the obvious crossing point, Allied engineers simply moved a few hundred metres up or downstream and built a Bailey bridge, where defences were weaker or non-existent. This tactical flexibility defeated German defensive strategy. Kesselring's forces could not fortify every possible crossing point along every river. They had to prioritise, establishing strong defences at major bridges and road junctions. Bailey bridges allowed Allied forces to ignore those strong points entirely, creating new crossing sites that bypassed prepared defences. The Gothic Line, Germany's final major defensive position in Italy, incorporated every natural obstacle in the northern Apennines. The line had taken months to construct, with bunkers, minefields, and artillery positions carefully integrated into the terrain. Allied forces breached it in 3 weeks during August and September 1944. Engineers built over 200 Bailey bridges across mountain streams and rivers during the breakthrough. German defenders found themselves constantly outflanked as Allied forces bridged obstacles that should have channeled attackers into killing zones. The speed of Bailey Bridge construction meant that German forces never had time to establish cohesive defensive lines. As soon as one position was fortified, Allied forces were already across the river behind it. General-Leutnant Fridolin von Senger und Ettelin commanded the 14 Panzer Corps in Italy. His post-war analysis, published as Neither Fear Nor Hope in 1963, dedicated significant attention to Allied bridging capabilities. "The Allied Bailey Bridge was a more effective weapon than any tank they deployed," von Senger wrote. "It negated our defensive advantages. We could no longer trade space for time by destroying bridges. The time we gained was measured in hours, not days or weeks. This fundamentally altered the operational tempo of the campaign. We were always reacting, never preparing." The Normandy invasion in June 1944 brought Bailey bridges to their most critical test. Allied planners knew that once forces broke out of the beachhead, the advance toward Germany would encounter hundreds of rivers and streams. German forces had already demonstrated in Italy and France in 1940 their willingness to destroy every bridge during retreats. The Allied solution was to bring overwhelming Bailey Bridge capacity. By D-Day, Allied engineer units had stockpiled enough Bailey equipment in Britain to build over 200 kilometres of bridging. The initial assault waves included engineer special brigades, whose sole mission was establishing logistics infrastructure, including Bailey bridges across any obstacles the breakout forces encountered. Within 2 weeks of the landings, British and American engineers had constructed over 40 Bailey bridges in Normandy. These bridges carried the entire logistics weight of 3 Allied armies. The scale of the operation was unprecedented. Every destroyed bridge was replaced within hours of its capture. German forces, attempting to delay Allied advances by demolishing bridges, found the tactic increasingly futile. By mid-July 1944, German situation reports began referring to Allied bridging capabilities as essentially unlimited. This was not accurate in absolute terms, but it reflected German perception that destroyed bridges no longer provided meaningful defensive benefit. The breakout from Normandy, Operation Cobra, began July 25, 1944. American forces punched through German lines and began a rapid advance across France. The advance maintained momentum largely because engineer units kept pace with combat forces, building Bailey bridges as fast as German engineers could destroy existing bridges. The Vier River, the Mayenne River, the Sarthe River, the Loire River, each represented a potential defensive line where German forces could establish positions and force costly crossings. Each was bridged within hours by American engineers using Bailey equipment. Lieutenant Colonel David Pergrin commanded the 291st Engineer Combat Battalion during the campaign across France and into Germany. His unit built bridges under fire, under air attack, during night operations, and in every weather condition imaginable. Pergrin's post-war memoir, First Across the Rhine, describes Bailey Bridge construction as the defining engineering challenge of the European campaign. "We built Bailey bridges until the process became automatic," Pergrin wrote. "Every man in the battalion could perform every task required for construction. We could start building in darkness, work through artillery barrages, and have a functioning bridge ready before daylight. The Germans learned they could not stop us by destroying bridges. They could only delay us by a few hours. That psychological shift, knowing they could not stop us, broke German defensive planning more effectively than any bombing campaign." The numbers support Pergrin's assessment. Between D-Day and VE Day, American forces constructed over 1,800 Bailey bridges in the European theatre. British and Canadian forces built approximately 1,200 more. These bridges carried every ton of supplies, every replacement soldier, every tank and vehicle that sustained Allied operations. Without Bailey bridges, the advance from Normandy to the Elbe River would have been impossible at the speed it actually occurred. German generals, interrogated after the war, consistently identified Allied bridging capability as one of the most significant technological advantages Allied forces possessed. Generalfeldmarschall Gerd von Rundstedt, Commander-in-Chief West from 1942 to 1945, stated in his 1946 interrogation that Allied bridging speed made defensive warfare impossible according to traditional doctrine. "We planned defenses assuming rivers would delay the enemy. This assumption proved false. The enemy crossed rivers as if they did not exist." The Rhine River crossing operations in March 1945 demonstrated Bailey Bridge capabilities at their absolute peak. The Rhine represented Germany's last major natural barrier. German forces had destroyed every bridge across the river except the Ludendorff Bridge at Remagen, which American forces captured intact on March 7th before it collapsed 10 days later. The Rhine was too wide for standard Bailey bridges. The river ranged from 300 to 600 meters across, depending on location, far beyond the maximum Bailey span of roughly 75 meters for the heaviest configuration. Allied engineers solved this by combining Bailey bridges with pontoon supports. Floating Bailey bridges used pneumatic pontoons or rigid pontoons as support structures, with Bailey panels forming the deck and trusses. This hybrid approach maintained the speed advantages of Bailey construction while extending span capabilities indefinitely. Between March 10th and March 31st, 1945, Allied engineers constructed 23 pontoon-supported Bailey bridges across the Rhine River. The longest stretched 620 meters and could support continuous tank traffic. These bridges were built under German artillery fire, under air attack from the few remaining Luftwaffe aircraft, and under constant threat of sabotage by German frogmen attempting to attach explosives to pontoons. Despite these challenges, no Rhine-Bailey bridge ever failed catastrophically. Several were damaged by German action, but engineer units had sufficient redundancy in design and materials to repair damage within hours. The Rhine crossings broke German defensive capabilities in the west. Once Allied forces established bridgeheads on the east bank, supplied continuously by Bailey bridges, German resistance collapsed. The Wehrmacht could not concentrate forces to eliminate the bridgeheads because any concentration drew immediate air attack and artillery barrage. They could not defend everywhere because Allied forces could cross the Rhine wherever engineers built bridges. The operational flexibility Bailey bridges provided meant that German forces never knew where the next crossing would occur. They had to defend the entire length of the Rhine, dispersing forces that might have been concentrated effectively if crossing points were predictable. By April 1945, the war in Europe entered its final phase. German forces retreated toward Berlin, destroying bridges methodically according to doctrine. Allied forces followed, building Bailey bridges methodically according to their own doctrine. The difference was that Allied doctrine worked. German doctrine assumed destroyed bridges meant time. Bailey bridges meant destroyed bridges were irrelevant. The strategic impact extended beyond the immediate tactical advantages. German defensive planning for the entire war assumed that rivers and terrain obstacles would channel enemy advances and create opportunities for defensive stands. This assumption shaped where German forces built fortifications, where they positioned reserves, and how they allocated limited resources. Bailey bridges invalidated those assumptions. Positions that should have been defensible became untenable. Reserves positioned to counterattack at river crossings arrived to find Allied forces already across and moving inland. Resources allocated to fortifying river lines were wasted because rivers no longer functioned as military obstacles. The psychological impact on German troops was profound and cumulative. Soldiers understood intellectually that their mission was to delay Allied advances. They were taught that destroyed bridges accomplished this mission. Then they watched Allied engineers build replacement bridges in hours. The frustration of conducting textbook demolitions that achieved nothing eroded morale as effectively as casualties eroded combat strength. Wehrmacht situation reports from late 1944 and early 1945 contain recurring references to enemy bridging superiority and inability to establish defensive lines due to rapid enemy crossing capability. These were not complaints about superior Allied tactics or overwhelming numbers. They were acknowledgements that the fundamental assumptions underlying German defensive doctrine had proven false. The Bailey Bridge, designed by a middle-aged British civil engineer who never wore a uniform, had achieved what tank armies and strategic bombing had struggled to accomplish. It had made German defensive warfare obsolete. The German response to Bailey bridges evolved through three distinct phases, each revealing how thoroughly the technology had disrupted traditional military thinking. Phase 1 was disbelief. German officers observing Bailey Bridge construction in North Africa and Sicily during 1943 initially assumed they were witnessing temporary footbridges, not structures capable of supporting armour. This misperception was documented in captured German intelligence reports from Tunisia. A Wehrmacht intelligence summary from May 1943 described British engineers as employing prefabricated footbridge sections of unknown design apparently suitable only for infantry crossing. The report concluded that British armour would still require conventional bridges, giving German forces time to establish proper defensive positions. This assessment was disastrously wrong. Within weeks, German units were reporting 30-ton Valentine and Churchill tanks crossing what intelligence had dismissed as footbridges. Phase 2 was recognition. By autumn 1943, German intelligence had obtained detailed information about Bailey bridges through captured equipment and prisoner interrogations. Wehrmacht engineering manuals were updated to include Bailey bridge specifications and construction methods. German officers studied the design, looking for weaknesses to exploit. They found very few. The modular nature meant destroying one section did not collapse the entire bridge. Engineers simply replaced damaged panels. The speed of construction meant German artillery had a window of only a few hours to interdict bridge building before the structure was complete and carrying traffic. Hauptmann Friedrich Sander commanded an artillery battery in Italy, tasked specifically with interdicting Allied river crossings. His post-war interrogation revealed the frustration of engaging Bailey Bridge construction. "We would range in on the construction site," Sander stated. "We would achieve good accuracy, landing rounds directly on the bridge structure or among the engineer crews. We would inflict casualties and damage panels. Then we would observe the construction simply continue. Damaged sections were removed. Replacement panels appeared immediately. New crews took over from casualties. Within 30 minutes, construction would resume exactly where it had stopped. We calculated that to permanently halt a Bailey Bridge construction, we needed to maintain continuous artillery fire for 3 to 4 hours. This required ammunition expenditure we could not sustain. Mathematics of interdiction were brutal for German forces. A single Bailey Bridge under construction presented a target roughly 60 meters long and 3 meters wide. At typical artillery ranges of 5 to 8 kilometers, achieving direct hits required sustained fire with substantial ammunition expenditure. Even when hits were achieved, the modular design meant individual panels could be replaced in minutes. German artillery doctrine emphasized ammunition conservation. Batteries carried limited basic loads, and resupply was increasingly difficult as Allied air superiority interdicted German logistics. Engaging a single Bailey Bridge could exhaust a battery's entire ammunition allocation. Then the battery would be out of ammunition when other targets appeared: infantry concentrations, armor formations, supply columns. German artillery commanders faced impossible choices: engage the bridge and run out of ammunition, or conserve ammunition and allow the bridge to be completed. Chose conservation. The bridges were built. Phase 3 was adaptation and failure. German forces attempted numerous countermeasures. They positioned demolition charges at likely crossing sites, attempting to crater approaches and make bridge placement impossible. Allied forces simply selected alternate crossing sites. They deployed frogmen and sabotage teams to attack completed bridges with explosives. Allied security measures, including underwater obstacles, patrol boats, and constant guard rotations, made these attacks largely ineffective. Of the hundreds of Bailey bridges built in Italy and France, fewer than a dozen were successfully destroyed by German sabotage. The most sophisticated German response was the development of specialized long-range demolition weapons. The Luftwaffe employed Fritz X and HS 293 guided bombs against bridges in Italy, achieving some success against large permanent structures. Against Bailey bridges, these weapons proved ineffective. The bridges were too small as targets, too numerous, and too quickly replaced. Even when a guided bomb did destroy a Bailey bridge, a replacement was operational within 24 hours. Oberst Hans-Georg Hildebrandt served as chief engineer for Army Group B in France during 1944. His responsibility included not just German bridge construction, but also assessment of Allied engineering capabilities. Hildebrandt's reports to headquarters, preserved in captured German documents, show the evolution of German understanding. In June 1944, immediately after the Normandy invasion, Hildebrandt estimated Allied forces could build 30 bridges per week across the theatre. By August, He revised this to 70 bridges per week. By September, he stopped providing estimates entirely, noting that Allied bridging capacity exceeds any meaningful measurement and must be considered unlimited for operational planning purposes. This assessment, unlimited bridging capacity, appeared in German situation reports with increasing frequency through late 1944 and into 1945. It was not literally accurate. Allied forces had finite Bailey equipment and finite engineer units. But from the German perspective, the distinction was meaningless. If Allied forces could bridge any obstacle they encountered within hours, the practical effect was the same as unlimited capability. The technical comparison between German and Allied bridging systems reveals why Bailey bridges were so dominant. The Wehrmacht's primary tactical bridging equipment was the Brückengerät B, adopted in 1939. Each BGB set could construct a bridge 16 meters long capable of supporting 16-ton vehicles. The system used steel trestle components that bolted together. Construction required specialized tools, trained engineer crews, and approximately 4 hours for a single 16-meter span. For longer crossings, multiple BGB sets could be combined, but this increased complexity and construction time proportionally. A 48-meter bridge required 3 sets and 12 to 14 hours to build. The BGB's weight was also problematic. Each set weighed approximately 3,500 kilograms and required a dedicated 3-ton truck for transport. Moving enough BGB equipment to bridge a major river required substantial logistical capacity. By contrast, a Bailey bridge of equivalent length and load capacity could be constructed in 4 to 6 hours by crews with minimal specialized training. Bailey panels could be transported on any standard cargo vehicle. Multiple trucks could carry enough panels for a 60-meter bridge. The logistics requirement was a fraction of German equivalents. More importantly, Bailey bridges could be rapidly reconfigured. Need more load capacity? Stack additional panels? Need to extend the span? Add more sections. The BGB offered no such flexibility. Once unconstructed, the bridge had fixed capabilities. German forces also employed the Brückengerät J, introduced in 1941 as a heavier solution. Each BGJ section was 8 meters long and could support vehicles up to 30 tons. Construction was even more complex than BGB, requiring hydraulic jacks and elaborate assembly procedures. A BGJ bridge took approximately twice as long to build as an equivalent Bailey bridge and required crews with extensive specialized training. The Kriegsbrücke, or war bridge, used by German forces for major river crossings, was a pontoon-supported structure, similar in concept to Allied floating Bailey bridges. German pontoons were well designed, but the deck structure used heavy timber beams that required cutting and fitting on site. This construction methodology was fundamentally slow compared to prefabricated Bailey panels. German engineer units could build Kriegsbrücke crossings, but construction time for a 200-meter river crossing ran to 36 to 48 hours under ideal conditions. Allied engineer units could complete equivalent floating Bailey bridges in 8 to 12 hours. The disparity was not in German engineering competence. Wehrmacht engineers were highly skilled and conducted numerous successful bridging operations throughout the war. The disparity was in design philosophy. German bridging equipment prioritized durability and reusability. Systems were built to be disassembled, transported, and rebuilt multiple times. This made sense in offensive operations where German forces would advance, build bridges, later disassemble them, and reuse the equipment at the next obstacle. Allied forces, particularly after 1943, operated under different assumptions. Bailey bridges were considered semi-permanent. Once built, they remained in place, supporting logistics indefinitely. When Allied forces advanced beyond a Bailey bridge, it simply stayed in place as part of the supply. Infrastructure. This meant Allied forces did not need to recover bridging equipment. They built forward constantly, supplied by industrial production that delivered new Bailey panels faster than engineers could construct bridges. German forces attempting offensive operations faced material constraints that made Bailey-style throwaway bridging impossible. They needed to recover and reuse equipment. This requirement introduced complexity and slowed construction. The fundamental irony was that German engineering doctrine, developed logically from resource constraints, made German bridging slower and more vulnerable precisely when speed and simplicity were most critical for defensive operations. March 7, 1945. The capture of the Ludendorff Bridge at Remagen has been well documented, but the Bailey Bridge operations that followed were equally decisive and far less known. When the Ludendorff collapsed on March 17th, killing 28 American engineers, the bridgehead held 25,000 troops with no heavy equipment. Everything depended on Bailey bridges. The 291st Engineer Combat Battalion had already begun construction before the Ludendorff fell, anticipating its structural failure. The tactical situation at Remagen was uniquely challenging. The Rhine at this point was 380 meters wide, with a current speed of 2.8 meters per second. German forces held the heights on both sides of the river, providing direct observation of any crossing site. Luftwaffe units, despite fuel shortages and Allied air superiority, were ordered to attack Remagen at any cost. Hitler personally demanded destruction of the bridges, diverting resources from other critical sectors. American engineers worked under conditions that revealed both the strengths and limitations of Bailey Bridge technology. The first tactical bridge, designated the Treadway Bridge after the equipment type used for deck sections, was not a pure Bailey structure, but rather a hybrid using Bailey panels for truss support with pneumatic pontoons for flotation. Engineers completed it in 32 hours, despite German artillery fire that caused 12% casualties among construction crews. The second bridge, named after Lieutenant Hugh Mott, who was killed during construction, was a true floating Bailey bridge. It used M2 pneumatic pontoons, spaced at 12-meter intervals, with doubled Bailey panels for deck and truss structure. Construction began March 10th at 2100 hours, and was completed March 11th at 0530 hours, 8.5 hours total. German artillery scored direct hits on the bridge twice during construction, destroying sections that engineers replaced within 90 minutes each time. What made Remagen exceptional was not any single bridge, but the systematic application of Bailey Bridge technology at industrial scale. Between March 10th and March 25th, American engineers constructed 9 separate bridges across the Rhine at or near Remagen. 6 were heavy tactical bridges capable of supporting continuous tank traffic. 3 were light infantry bridges. The longest, the Pershing Bridge, measured 620 meters and used 51 pontoons with triple-stacked Bailey panels to support 42-ton M26 Pershing tanks. German forces attempted sustained interdiction. Artillery fired over 8,000 rounds at Remagen bridges during the 2-week construction period. Luftwaffe pilots flew 367 sorties, including jet-powered Arado R-234 bombers, specifically allocated to bridge destruction. German frogmen made multiple infiltration attempts to plant demolition charges on pontoons. Despite these efforts, not a single Remagen bridge was permanently destroyed. Several were temporarily damaged, but engineer crews repaired all damage within hours. The engineering achievement was staggering in statistical terms, but the strategic impact was what mattered. The Remagen bridgehead allowed American forces to establish a lodgment east of the Rhine before German forces could organize coherent defenses. First Army poured 25 divisions across the Bailey bridges in 2 weeks. These divisions became the spearhead for the final Allied drive into Germany's industrial heartland. The Ruhr pocket, encircled and captured in April 1945, resulted directly from operations that began at Remagen. German generals understood precisely what had happened. Generaloberst Alfred Jodl, chief of the operations staff of the Armed Forces High Command, stated during his Nuremberg trial testimony that the Rhine crossings demonstrated that Allied engineering capability had rendered river obstacles militarily irrelevant. We could no longer trade space for time using natural barriers. The operational flexibility this gave Allied commanders was decisive. The human cost of Bailey Bridge operations has been under-examined in popular histories. Engineers building bridges under fire suffered casualty rates comparable to infantry assault units. The 291st Engineer Combat Battalion, which built more Rhine bridges than any other single unit, lost 47 men killed and 189 wounded during bridge operations at Remagen alone. These casualties occurred not during combat maneuver, but during the mechanical work of assembling bridges while exposed to artillery fire. The nature of bridge construction made casualties inevitable. Panels had to be lifted, positioned, and pinned together regardless of incoming fire. Engineers could not take cover without halting construction, and halting construction extended time in the kill zone. American doctrine accepted these casualties as necessary. Speed of construction was prioritized over protection. The faster a bridge was completed, the fewer total casualties would result. Slowing construction to minimize casualties simply extended exposure time and increased total losses. British engineer units employed slightly different doctrine, emphasizing smoke generators and suppressive fire to protect construction crews. This reduced casualties but increased construction time. American forces calculated that accepting higher casualty rates during rapid construction resulted in lower total casualties across the entire operation because bridges entered service sooner, allowing follow-on units to cross under less fire. These calculations were ruthless but mathematically sound. A bridge that took 8 hours to build might cost 12 casualties during construction. A bridge that took 12 hours to build might cost 8 casualties during construction, but 30 casualties among units waiting to cross while under artillery fire. The total casualty count favored rapid construction despite higher immediate engineer losses. German engineer units faced similar mathematics with worse outcomes. Building bridges with more complex equipment under resource constraints meant longer construction times. Longer construction times meant extended exposure to Allied artillery and air attack. German engineer casualties in the West during 1944 and 1945 were proportionally higher than American engineer casualties, despite Allied forces conducting far more bridging operations. The post-war assessments by German military leadership were remarkably consistent. The Bailey Bridge, more than any other single technology, had defeated German defensive strategy in Western Europe. This conclusion appeared in interrogations, memoirs, and formal military analyses conducted by the United States Army Historical Division. General Feldmarschall Albert Kesselring, who commanded German forces in Italy and later in the West, provided perhaps the most comprehensive assessment. In his memoir, published in 1953, Kesselring wrote, "The Allied Bailey Bridge revolutionized warfare in a way few recognized at the time. It made defensive operations based on natural obstacles obsolete. Our entire strategic concept for defending Italy and later Germany rested on the assumption that rivers and mountain barriers would channel enemy advances and create opportunities for counterattacks. The Bailey Bridge invalidated this assumption. The Allies could cross any obstacle within hours. Our defensive preparations were bypassed. Our reserves arrived too late. The operational tempo favored the attacker absolutely." General Lieutenant Fritz Bayerlein, who commanded Panzer Lehr Division in Normandy, made similar observations. "We could not establish defensive lines because rivers ceased to function as military obstacles," Bayerlein stated in his 1946 interrogation. "The Americans would reach a river, and before we could fortify the opposite bank, they had bridge across and were already moving inland. Our doctrine required 72 hours to establish proper defensive positions. The Bailey Bridge gave us 4 to 6 hours. This made textbook defense impossible." The strategic implications extended beyond individual battles. German defensive planning for the entire Western Front after Normandy was compromised by Bailey Bridge capabilities. Forces that should have been concentrated at critical river barriers had to be dispersed across broad fronts because Allied forces could cross anywhere. Reserves that should have been positioned to counterattack at predictable crossing points had to be held further back because crossing points were no longer predictable. This dispersal of forces and dilution of defensive effectiveness resulted directly from one technology that changed the fundamental nature of river obstacles. The legacy of the Bailey Bridge extended far beyond World War II. The design proved so successful that it remained in service with military forces worldwide for decades. During the Korean War, American and British forces used Bailey bridges extensively. The same panels and components that crossed rivers in France and Germany in 1944 crossed rivers in Korea in 1951. The Vietnam War saw continued Bailey Bridge employment, though by this time aluminum panels had largely replaced steel to reduce weight. The modular principle remained unchanged. The modern successor to the Bailey Bridge, the medium girder bridge, used by NATO forces, directly descended from Bailey's original design. The component dimensions changed. The materials evolved from steel to aluminum to composite materials, but the fundamental concept of identical, interchangeable, pin-connected panels remained the core of military bridging doctrine. Civilian applications proved equally significant. Surplus Bailey bridges after World War II were sold to developing nations and remote regions where conventional bridge construction was impractical. Australia deployed Bailey bridges across Papua New Guinea, where some remained in service into the 1990s. African nations used Bailey bridges to establish rural road networks. The simplicity of the design and minimal requirement for specialized construction equipment made Bailey bridges ideal for infrastructure development in regions lacking industrial construction capacity. Disaster relief organizations maintain Bailey bridge stockpiles specifically for emergency deployment. When earthquakes, floods, or infrastructure collapse cut transportation networks, Bailey bridges provide rapid restoration of critical routes. The 2010 Haiti earthquake response included Bailey bridge deployment. The 2011 Tohoku earthquake in Japan saw military engineers use modular bridges based on Bailey principles. The design that won World War II continues saving lives in peacetime emergencies. Donald Bailey received remarkably little public recognition during his lifetime. He was knighted in 1946, becoming Sir Donald Bailey, but remained largely unknown outside engineering circles. He never sought publicity and rarely gave interviews. Bailey died in 1985 at age 84, having watched his design used across every continent and in every conflict since World War II. The obituaries noted his contribution but could not adequately capture the magnitude of his achievement. Bailey had solved a problem that had plagued military engineering for 2,000 years. He had made bridge construction simple enough for ordinary soldiers, fast enough for battlefield conditions, and reliable enough to stake entire campaigns upon. The impact was global and permanent. Modern military engineering doctrine still teaches Bailey Bridge principles. The United States Army Engineer School at Fort Leonard Wood includes extensive instruction on rapid tactical bridging. British Royal Engineers study Bailey Bridge operations in Italy and France as exemplars of engineering supporting maneuver warfare. The specific equipment has evolved, but the underlying philosophy, simplicity, modularity, speed, remains the foundation of military bridging doctrine worldwide. The broader strategic lesson concerns the nature of technological advantage in warfare. The Bailey Bridge was not a sophisticated technology. It used no advanced materials, no complex engineering principles, nothing that was not available in 1940. What made it decisive was not sophistication but optimization for the specific requirements of military operations under combat conditions. German bridging equipment was in many respects more elegant, more reusable, more technically refined. Bailey bridges were simpler, faster, and more suitable for the operational requirements Allied forces faced. This pattern repeated throughout World War II. The side with adequate technology, produced in overwhelming quantities and optimized for actual combat conditions, defeated the side with sophisticated technology produced in limited quantities and optimized for theoretical performance. The Bailey Bridge epitomized this principle. German forces brought craftsmanship and technical excellence to bridge engineering. Allied forces brought industrial production and design simplicity. Industrial production won. The psychological legacy affected post-war German military thinking profoundly. The Bundeswehr, established in 1955, adopted NATO standards for bridging equipment, which meant adopting Bailey-derived systems. Former Wehrmacht officers, now serving in the Bundeswehr, found themselves using equipment based on the same principles that had defeated them. This represented a fundamental acknowledgement that the Allied approach to military engineering had been correct. The Rhine crossing operations at Remagen became required study material at military academies worldwide. The combination of surprise, engineering skill, and operational exploitation demonstrated how a single, successful river crossing could unravel an entire defensive front. Modern military doctrine emphasizes rapid bridging capability as essential for offensive operations, a direct legacy of lessons learned in 1945. For German soldiers who faced Bailey bridges in combat, the memory remained vivid decades later. Veterans interviewed in the 1980s and 1990s consistently identified Allied bridging capability as one of the most frustrating aspects of fighting the Western Allies. The knowledge that destroyed bridges meant nothing, that every river would be crossed within hours regardless of demolition efforts, created a sense of futility that eroded effectiveness as surely as casualties depleted strength. This psychological erosion was cumulative and ultimately decisive. German forces conducted technically proficient defensive operations. German officers made sound tactical decisions based on doctrine. German soldiers fought with courage and skill. None of this mattered when the fundamental premise of defensive warfare, that natural obstacles provided time and space to organize resistance, proved false. The Bailey Bridge had broken that premise. Once river obstacles ceased to function as barriers, German defensive strategy collapsed. The final irony is that German intelligence had identified Bailey bridges as early as 1942. Captured equipment was studied, the design was analyzed. German engineers understood how it worked. What they failed to grasp was the strategic implication of having such technology available in unlimited quantities. Knowing that Allied forces possessed Bailey bridges was different from experiencing what it meant when every Allied division included engineer units trained and equipped to build them. The gap between intellectual understanding and operational reality destroyed German defensive planning. They knew Allied forces could build bridges quickly. They did not comprehend that this meant rivers no longer functioned as military obstacles. They adapted tactics to account for Allied bridging speed. They did not adapt strategy to account for the obsolescence of defensive lines based on natural barriers. By the time German High Command recognized the full strategic implications, usually in mid to late 1944, it was too late to develop effective countermeasures. The Bailey Bridge won World War II, not through dramatic battlefield action, but through the quiet elimination of German defensive advantages. Every river that should have provided days or weeks of respite instead provided hours. Every defensive position that should have been secure behind a water barrier became vulnerable to flanking movements. Every operational plan that assumed time to prepare became obsolete before implementation. The cumulative effect across hundreds of river crossings, thousands of Bailey bridges, and 2 years of sustained operations was the collapse of German defensive capability in the West. Not a sudden dramatic collapse, but a gradual erosion, as each defensive position failed earlier than planned. Each retreat began sooner than intended. Each counterattack arrived later than required. The mathematical accumulation of these small-time advantages overwhelmed German forces, despite tactical proficiency and fighting skill. In the end, the Bailey Bridge proved what Donald Bailey had always believed. Complexity was not strength. Simplicity was strength. The ability to train ordinary soldiers to build bridges in hours was worth more than sophisticated systems that required specialists and days. The capacity to produce thousands of identical components was more valuable than craftsmanship that produced hundreds of unique assemblies. The willingness to treat bridges as expendable and build forward constantly was strategically superior to careful recovery and reuse of expensive equipment. These were industrial-age principles applied to military engineering. They violated traditional military values of efficiency, craftsmanship, and resource conservation. They worked because modern warfare was industrial warfare, and industrial warfare rewarded mass production over quality, quantity over sophistication, adequate performance in vast numbers over excellent performance in limited quantities. The Bailey Bridge embodied these principles completely. It was the physical manifestation of how the Allies fought World War II and why they won. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.